Welcome back to Statics. This is ENGR 214 ampersand Bellingham Technical College Winter 2020. And in this lecture we are going to derive and then use in a couple of examples the equations for shear and bending moment for a vertically loaded beam as a function of distance along the beam from one supported end. So to start out, we're going to take a step back and take another look at internal forces in a more general sense. We started this in the last lecture on internal forces, and so we're going to pick up with a bit more. So this time, rather than any kind of particularly shaped two-dimensional member, we've got a 3D body with any number of forces and applied moments. Remember, the double arrow is a moment or a couple. And we want an expression for the internal force at any section plane in this body. This is a big 3D blob, and we're going to section it along this plane here. So we do that, and we have it separated into two rigid bodies, and we can represent, using Newton's third law, the resultant force and moment that each one exerts on the other. So basically, this moment is the torque effectively being exerted on the left-hand body by the right-hand body, and this force is the force being exerted on the left-hand body by the right-hand body. And of course, given Newton's third law, those are equal and opposite. That's great. It is more useful to us, as we saw in the last lecture, to resolve that force and moment into components that are parallel and perpendicular to the section plane at the point of interest. And we only had one resultant moment that we dealt with in our 2D example last time. This time we're going to look at our 3D case. Even though we won't work a lot of problems in 3D, actually we will not work any in this course, but be aware that they exist, and that if you needed to get shear and bending moment at any point in a beam that was being loaded in two different orthogonal or three different orthogonal directions, all you would have to do is do what we're doing for a 2D case and then repeat it for each one of the other orthogonal directions and add the resultant moments and shear forces and axial forces as vectors. Vector addition to the rescue, and since they're being applied in different orthogonal directions, they'll just end up being additive for a resultant. They won't add to themselves because they're in separate orthogonal directions. Okay, you will not deal with that in this course, but we will look at it in this general case so you're ready to on the job. So we're looking again at our cut body from up here, left-hand section, and we're going to create a point A on that section, and we're going to take this moment and this force and just resolve them into three orthogonal directions. So we get a component of the force that is in this orthogonal direction, which we just happen to have defined as being perpendicular to the cut section, and then that same force F will have components in the other two orthogonal directions, which are parallel to the cut section, so they're within plane. Same thing with the moment. We can define the moment vector as having one component perpendicular to the cut section and then two other components that are orthogonal to each other, parallel to the cut section, and therefore orthogonal to the first. So F sub 1 ends up being the normal or axial force, so it's going to be the one that is either putting this body into effective tension or compression, and F2 and F3 are both shear forces, again in opposite orthogonal directions. M sub 1 as a moment will make the body twist around the axis that is longitudinal here, and then M sub 2 and M sub 3 will create flexion or bending out of plane of the paper and then in plane with the paper. So if you have a slender member, which unlike a two-force member for a truss, can carry shear, axial, and twisting or bending loads. Remember, in trusses we only had axial. If you can carry all three, you've got a beam. And slender is less important for beams than it was for trusses. We no longer have to make assumptions that these members can't carry shear and bending because they very much do. So a word about sign conventions. When we cut a body or we cut a beam and we start assigning these forces outward from the cut section, we'll be talking in terms of a right-hand face or a left-hand face. Most of the derivations and beam bending type of equation derivations and uses are for a right-hand face, because we typically define the positive x direction as going from left to right. That's just basic sign convention in Cartesian coordinates. So you'll typically be working with a right-hand face. You can work with a left-hand face as well. And in fact, we'll be picking up that left-hand face as we derive the differential equations relating shear and bending. Okay, so here's our sign conventions. If you are looking at the right-hand cut face, normal force is positive if it's would effectively be putting the remaining member in tension. If it's pulling outward, it's directed outward from the cut face, not towards the body, but outward from it. Shear is in the upward direction, and bending, the applied moment, is counterclockwise. And if you're integrating and you're deriving equations for the left-hand face, again, normal force is in tension, but because it's on the left-hand face, it's opposite in sign. If you had an absolute coordinate system outside of the beam, shear is going now downwards and moment is going clockwise. Okay, so what we really want to do at this point is get an expression for shear and bending moment for a beam that might have a distributed load, might have some point loads, definitely is going to have support reactions, and we want to get an expression for shear and an expression for bending that is in terms of an x location along the beam. And I got to apologize for my free body diagram here with all the different expressions for shear and bending at 2 points, but please imagine that you have a beam that is running from right to left along the page, and we are looking at 2 locations along the beam, one location at x and one location at x plus delta x. So we have effectively defined a delta x width of beam. So it's kind of a little square here defined. I'm moving my cursor to define it, a little bit of beam. But the delta x direction goes between this point at x and at this point at x plus delta x. So the distance between them is delta x wide. We don't have to worry about how thick the beam is or how deep it goes because we're considering it to be slender. So we don't have to worry about rigidity and moment of inertia on the cross section, all those things that you would worry about if you were going to actually design the beam. We're just going to load it. So we only need to worry about the x direction. Okay, so we have a differential element. Just like we did with the capstan equation, we're going to take that differential element and we're going to load it up, and then we're going to apply the conditions of equilibrium, sum of the forces in the x, the y, and the z. It's two dimensions, so we only have x and y, and then we're going to look at the bending moment about point A that's out there on the cut face. So we're imagining that we've got a little slice of beam here, and we've cut it on the right hand side, and then we've also cut it on the left. So we have like a freestanding little delta x width element of beam. And we're going to define point A as being a point on that cut right hand side. So when we take our sum of the moments and we put this little volume element of beam in static equilibrium, we're going to take our moments about that point. Okay, as it just so happens, this beam has a distributed load, an upward distributed load that's defined by some function q, which is a function of your location x. So the value of the distributed load in like newtons per meter or something at x is q at x, and over here it's q at x plus delta x. Maybe it's a little more, a little less. Okay. So effectively this little volume element is being prevented from accelerating under the influence of this distributed load by by all of the forces and moments being applied by the cut side on the right that we cut away and the cut side on the left that we cut away. So the only directly applied loads that we have on this volume element is the distributed load, which is a function of x. So everything else is an internal load being applied by the cut away parts of the beam to the left and then to the right. So let's just tally up those forces here. So being contributed by the now missing left-hand side of the beam that we cut away, we have a shear force V acting at x, and V changes with x, but this is V at point x. We've got a tensile force, axial, represented by an N at point x. So who knows how that varies, but we know at point x it's N at x. And then likewise we have a moment, which is M also at x. So notice everything is relative to the location on the beam in the x direction. Okay, so over here at point A, we are now at location x plus delta x, and of course we have the same corresponding suite of forces being applied by the right-hand side beam that we cut away at location x plus delta x. So we have an N, and this should really be an N. It's misdrawn a bit there. This was drawn on the bus, so apologies for the less than perfect handwriting. So this is normal force at x plus delta x. We've got a moment going in the counterclockwise direction of the amount of some function m at x plus delta x. And of course we have shear at in the amount of some function v at x plus delta x. And of course we've also got our distributed load, which we would have to represent with an integral. It would be really nice now, the rest if we wanted, backing up a bit, if we wanted to write the equations of equilibrium, with the exception of that distributed load, everything's pretty straightforward. If we looked at the sum of the forces in the x direction, we would just have n at x plus delta x minus n at x. And then our y forces would be negative v at x plus v at x plus delta x plus the integrated distributed load between x and x plus delta x. So if we had a function q for that distributed load, that wouldn't be too hard. All we'd have to do is integrate q between x and delta x, and we'd have an effective resultant force. We wouldn't quite know where to apply it, but if we're only taking the forces in the y, it doesn't really matter. Now where it matters is when we start taking moment. Our third equation of equilibrium is going to say, well, let's make sure that the moment about any point on this body, in this little differential body that's of a width delta x, we're going to take it around point A. That's got to equal 0. So we don't have to worry about any of the forces that are being applied at A. So this goes away, that goes away. Even though it's shown offset, it's really acting through point A. So what we've got is v sub x, which is going to produce a positive moment about A, equal to v sub x times delta x, because delta x is the distance from A that v sub x is acting. We are assuming that n sub x is going to act on a line through A, so it doesn't produce a moment. So that only leaves a positive moment m sub x and a negative m at x plus delta x, and those are location independent. Then we've just got the moment due to this upward distributed load. So we said we could take the integral, if we had the function q, we could take the integral from point x to point x plus delta x. We can integrate the function between those 2 points as a definite integral and evaluate it, and then we'd get the magnitude of the resultant upward force over this distance. The problem is we'd need an expression for the resultant. Well, in the past when we looked at equivalent resultant distributed loads, we use the sum of the moments to get the resultant location. Here that's a little bit muddier because we've got this differential element. We don't always have a function of q at x. So we're going to use another kind of equivalent treatment of the moment due to this distributed load, and we're going to invoke the mean value theorem from calculus. And that says somewhere on this interval from x to x plus delta x, there's some value of x, there's some position for which the value of the function, and this is the distributed load function, the q sub x, or q in this case q sub of x plus this delta, which gives us a location. So it gives us a function of value at that location times the full width of the integral that's equal to the complete area under the curve. So this is another way of saying basically there's an equivalent rectangle that equals the same area as the exact area. If we put that if we put the height of that rectangle at just the right location as defined by the y value of your distributed load function, and then multiplied by the width of the rectangle, which is our delta x, we'd get something equal to the full area under the curve, which is effectively our resultant force. Aha! That effectively says this delta, which is somewhere between x and delta x, that's the position of our equivalent resultant force produced by that distributed load. That's kind of convenient. So we can pop those into the integral, define it at x and x plus delta x, take this, divide it over, and say that's effectively equal to the average value of the distributed load between x and delta x. It's another way of expressing that function. That allows us to say that this integral, which we've now included an expression for x in, this is now our moment. If you remember, this is our moment due to the distributed load, is going to effectively be equal to our function value times that offset position and our width. So q sub 1, which is effectively our distributed load function, it's going to act at a location delta here, which achieves the same moment as the distribution. So here's the moment back from our distributed loading equivalent. So that's the equivalent moment. We can say that'll be hard to get given that we're already working in a differential element somewhere on a beam, but we can say that that's equal to this position location times q1, which is the value of the average value of the function, the distributed load, times delta x. Walking through this, we are going to use this in the moment expression. We're going to put this in as part of our sum of the moments when we do the equilibrium analysis and see what happens. So we have a position, we have a function value for the distributed load, and then we have the width, delta x. And we'll see what happens to that when we start squeezing delta x down. Let's tally up forces in the y. So we're going back to our free body diagram of our differential element. So we're going to tally up everything that's in the y direction and bring it down here. So we ended up having our shear at position x plus delta x plus our average value of our distributed load times the width of our differential element. So that gives us a force, and it's heading up, minus the shear force evaluated at point x, which was heading down. So this gives a little bit of insight into how this average value is working. Okay, those all sum to 0. Now we're going to write out moment. So we have a positive or counterclockwise moment being applied from the right-hand side beam that we cut off, which is our m at x plus delta x here. We have corresponding moment in the clockwise direction that's being applied by our cut-off left-hand side here. We have the effective moment due to the shear force that is acting specifically at point X, position X on that left-hand side, times the radius that it's acting on from point A, which is delta X. So that's R, which is in this case delta X, times V sub X, and that's going to produce a positive moment. Then we have the moment due to our distributed load, which is the average value of our distributed load over x plus delta x times delta x, the width over which it's applied, times that magical position which effectively gave us the average value. And if we do a units check, you can remember that Q sub 1 should be in something like newtons per meter, delta x should be in meters, and then this delta function will also, being positioned, will be in meters. So this has got the correct units. And it's got a negative sign because it's heading up and would produce effectively a clockwise moment. And we've defined that to be negative. Okay, now we're going to take these expressions and we're going to look at what happens when we rearrange them and then squeeze delta x to 0. So we're going to go back to the top of the page. This is written a little bit different. You can take the sum of the forces in the y and you can do a little rearranging, a little algebra on it, and get this expression. You can get v at x plus delta x minus v at x over delta x equals negative q1. This should look real familiar to anyone who's taken differential calculus. This is effectively the definition of derivative of v with respect to x. So dv dx equals negative q1. So that will become true when we shrink delta x down to 0, taking the limit of this as delta x approaches 0. So we can say the derivative of the function of shear force as a function of x with respect to x equals negative q of x. And q in this case is being defined upward. Obviously, if q of x was being defined downward, we'd drop the negative sign. Okay, let's do the same thing with moment. We'll do the same rearranging. We'll get, basically, now that we know we are looking for a definition of derivative, we're going to clump all the terms that are our moment as a function of x, or x minus delta x, and then divide everything through by a delta x. And you can see back here, everything, these two had delta x multipliers. So all we were really doing is moving these two terms, or keeping them on one side, taking the other two terms to the other side, dividing both sides by delta x, just a little algebra. So we end up with effectively dm dx equaling negative v of x. So first derivative of moment with respect to x is equal to the shear function. Shear force is a function of x, negative, plus q1 times delta. Okay, and this is still in the differential, it's in the delta x. We haven't squozen delta x down, but we've got q1 times delta. So now we're going to squeeze delta x down to 0 and take the limit of everything as delta x goes to 0. So we know that effectively there's no delta x here, so the limit of this as delta x goes to 0 is just this. The limit of this side as delta x goes to 0 is dm dx. What happens to this as delta x goes to 0? That's kind of the $64 question, because that tells us what we need to do with the distributed load. Well, as it happens, as delta x gets really, really small, the average value of that distributed load times this kind of position, delta position, also goes to 0. And if you want to think about it, you can think about this position as being some fraction of delta x. So this is representing, basically some, where within delta x are we applying our average position? Well, if delta x is 0, delta is even less than delta x. So this is one of those, I think it's called a squeeze limit. So that you can say that that this delta function is less than our delta x. So if delta x goes to 0, the delta goes to 0 even faster. So it definitely goes to 0. So you end up with q1 times 0. So this term goes away. So we went to all that trouble to define the resultant moment only to have it disappear in the limit as delta x goes to 0. Fine, gives us a nice simple expression for moment. So these two are key, and the sign here for the first derivative of shear with respect to x being equal to the distributed load, this negative sign will be there or not depending on which direction you are defaulting the distributed load. If the distributed load is downward, which it really quite often is, you won't have the negative. So be aware of how we derive this. If we're talking about weight or some kind of loading that you're supporting against gravity, the distributed load would be downward and then this negative sign would go away. This negative sign, however, is inherent to the definition given the assumptions for positive values on right-hand and left-hand side. So never forget that. This one is going to be independent of your distributed load direction, especially because distributed loads went away. So these are your two kind of workhorse go-to equations. Apologies to those of you who are maybe new to calculus, but this is differential calculus, and in fact this is real basic definition of derivative and understanding of limits. So we're harnessing those real fundamental mathematical concepts directly to give us a real easy to use expression for shear in terms of a distributed load on a beam for any x position from one side to the other. And then moment, once we found shear, then all we have to do is integrate again and we can get moment. So these are the differential relationships between a distributed load, a shear force at any position, and a bending moment at any position on a beam. So now that we have these great expressions, we're going to put them to use. So we've got two examples here and a warning as you work ahead on your homeworks and you prepare for the exams. These are very long problems. The exam is going to give you plenty of time, but as you practice these, please leave yourself plenty of time to do them. So there'll be a lot of math to do. Again, it's not complicated. There's not a lot of intuitive leaps, but there are a few that I'll point out as we go through these example problems. But with that exception, this is going to be a lot like method of joints, where you just kind of turn the crank over and over, recognizing some initial and final conditions, and be rigorous. Okay, so we've got a beam. It's simply supported. So you have a support here at point P and R. P can apply loads in two directions, Y and the X, and R can only apply loads in the Y. So we have three potential forces that we can get from the support reactions. And we have a distributed load that acts from point X equals 4 feet to point X equals 10 feet there at the end. So as usual, our first step here is going to be to find the reaction forces at the supports. And once we have those, we're going to start over here at the left-hand side. We're going to use our left-handmost support reaction to create an x equals 0 condition for shear. and then we're going to integrate forward along this open section, and we're going to see what happens with the loads that are applied by the cut off right hand side of the beam that we're going to cut off. See how those applied internal forces change as we move from x equals 0 to x equals 4. Then we're going to start up a new section, and we're going to take all of the initial conditions at the start of the new section from whatever we had at the end of the old one, and it's going to handshake over into our limits of integration. And we're going to rock on with a Q, and we're going to integrate to get a V, and we're going to integrate to get an M, and we're going to express those as a function of x from x equals 4 to x equals 10, and we're going to hope to goodness that our end condition corresponds to whatever our support reaction is here from R, and we better not have a moment that we're saying is present at x equals 10, because as you can see, this is free. This is not a moment applying support. So there's nothing to apply a moment, so we better not find that we need one. So that's where your internals checks come when you define or you solve your equations for moment and shear at your end and see if the support reaction applied at that end is capable of applying that. Okay, so back to the support reactions. The first thing we need is to find the resultant load, the single point resultant load of this distributed load, not for the purpose of seeing internal forces, because a point load won't do that, but just to get our support reactions. So we'll go ahead and integrate our 150 pounds per foot between 4 feet and 10 feet, and we will get a negative 900 pounds. We'll go through the same exercise to find its resultant moment, integrating that negative 150 pounds per foot times x between 4 feet and 10 feet, and the limits of integration really matter here. We're going to start slapping a coordinate system on at the very beginning of the beam, so it's not relative now. We need to be careful to reference everything back to what we've decided x equals 0 is. So x equals 0 is over at point P. So we're going to integrate negative 150 pounds per foot times x with respect to x between 4 feet and 10 feet. And so we integrate a polynomial, plug in our limits of integration, and we find that we get a resultant moment from this distributed load equal to negative 6,300 foot-pounds. And we can use that. We can use the total resultant force from the distributed load and use that to solve the hinge forces at P and at R. So P of x is 0 because there's no horizontal loads being applied. We've got an upward force being applied at R in an amount of 630 pounds, and we have an upward force at P of 270 pounds. Okay, so now we know what's happening kind of on the outside. Now we're going to start at x equals 0, and this little symbol of sort of the wall with an x going forward means this is the 0 point of x right here, and x will increase as you go to the right. So this is like a 1D coordinate system. So we're going to do the same thing we did with internal forces in the previous lecture. We're going to cut the beam off somewhere between x equals 0 and x equals 4 feet. And we're going to represent the loads coming from the cutoff section with our favorite shear and bending moment, which are going to change with x. So we're just going to write them with our positive convention. We're on the right hand cut face, so v sub x is positive going upward, and applied moment is positive counterclockwise, and we've got our 270 pound supported x. Q sub x is 0. Okay. So from x equals 0 to x equals 4 feet, this is the section we're concerned with. So we're gonna look at everything piecewise. Piecewise integration. So Q sub x is 0. So if I take the integral of Q sub x dx with respect to x, I'm taking the integral of 0 with respect to x. Well, what do I have to take the derivative of to get 0? A constant, any constant, okay? So I can say that the shear force is a function of x between x equals 0 and x equals 4 feet is a constant. What constant is it? Negative 270 pounds. Because v sub x would have to be a negative 270 pounds to balance this. So v sub x is a constant all the way through here. Okay, that's great. So v sub x anywhere is negative 270. And just for good practice, because I'm going to need to know it for my starting point in the next section, I'm just going to go ahead and do the trivial solution and define shear at 4 feet is negative 270. So it's negative 270 anywhere. Okay, so let's pick up moment. So moment is defined as negative integral of the shear force as a function of x with respect to x. Okay, what's v sub x? Negative 270 pounds. So negative integral of negative 270 pounds with respect to x is going to be negative, and a negative makes a positive. That's 270 pounds times x plus some constant. Okay, we can evaluate the constant by taking the moment at 0, which was 0. Why? Because the hinge can't apply a moment. There was no moment being applied at x equals 0. So this constant has to be 0. So the moment anywhere at any x between x equals 0 and x equals 4 feet is 270 pounds times the x position. If I wanted to know what it was at 4 feet, I just put in 4 feet for x and I would get positive 180 foot-pounds. So definitely, by the time we get to 4 feet, that cutoff right-hand section is applying a fair bit of moment to our left-hand section. Okay, so we know everything that's going on inside the beam in terms of shear and bending between our point P and where we begin to pick up the distributed load. We've got a constant negative 270 pound shear force, and we have a linearly increasing moment. Okay, what happens between 4 feet and 10 feet? Well, we know that our distributed load is going to be a factor. And because we've now indexed our coordinate system back here to the back end of the beam, we need to write an expression for q sub x that's referenced back here. So our original expression really was kind of faking it. We kind of slapped on a temporary coordinate system where x equals 0 was right here at the beginning of the distributed load. Well, if we want to index everything back to P, we can't use this because that would be telling us our distributed load picked up right here. So we've got to put in some kind of offset that says we don't start applying that distributed load until x gets to be a certain value. So we're going to define the distributed load as a q at x minus 4 feet. So and we're going to say it's undefined for a negative value of x. So this doesn't even exist until x gets to 4 feet, which is exactly what we're doing up here. So that's the mathematical way of saying don't apply anything until we get to 4 feet. And then we use the constant distributed load. Okay. So now we're defining everything in terms of x minus 4 feet. So we can go into our definition of shear force in terms of a downward applied distributed load. So if we had an upward applied distributed load, we would have a positive excuse me, let's go back and check our sign convention. What did we get? For an upward distributed load, we had a negative. So let's check our signs here. So we're retaining the negative sign and we're going to drop in the 150. Okay, so a shear force at any x minus 4 feet is going to be the integral of a distributed load times what we're integrating with respect to. So we've now substituted an x minus 4 feet for x in everything to show that indexing over. We're doing this, by the way, we're doing this indexing because we're not using definite integrals. We're using indefinite and popping out an integration constant. We'll get away from this substituted offset when we go to definite integrals. It'll get a little bit easier. So we basically crank through the integration and end up with 150 pounds with signs canceling times x minus 4 feet plus some constant of integration. So distribute the 150 pounds across x minus 4 feet, and then 150 pounds per foot times C3 is just another constant. And so we use our limit from our previous section to evaluate C3. We can say, well, what is V at 4 feet? It was negative 270 pounds. So I can say when x is 4 feet, V is negative 270 pounds. So if I put in 4 feet for x, this whole term goes to 0, and I can evaluate x at 4 feet is negative 270 pounds equals C3. So I can rewrite that with the constant equipped. V at x minus 4 feet equals 150 pounds per foot times x minus 4 feet minus 270 pounds. So now I'm going to input 10 feet and see if V reproduces my support reaction, because it needs to, because by the time I get out here there is no remaining right hand side to provide that upward V sub x, so the support needs to take the place of the right hand side, which is no longer there. So if I put in 10 feet and solve for it, I find that I do get the positive 630 pounds. So that's a good check. That also tells me I am safe to use this expression, well, what is effectively this expression, with my constant solved, integrate it to get moment. So just to back up a little bit to take a look at what did our shear expression look like. This time, rather than having a constant shear force internal in the beam over the section from 4 feet to 10 feet, I had a linearly increasing shear force. So shear was going up. So my maximum shear, if I wanted to know where the shear force in this beam was a maximum, it was a maximum right before I hit the right hand support. So that's where I would need the most transverse reinforcement, is in that area. Okay, now I want to get bending. So I'm going to integrate my shear expression with respect to x. I'm going to throw a negative sign out in front because moment is always negative of the integral of our shear force with respect to x. And so I'm just going to drop these same expressions in and integrate. This is my integral, my indefinite integral with our constant of integration. I'm going to go back to what was my moment at 4 feet from my previous section. I'm going to use that term to solve for C4, just some algebra. So I'm going to put in 4 feet here. This is going to be my substitution, and I get 180 foot-pounds for my constant. So when I put in 4 feet for here, that becomes a 0 and that term goes away. I put 4 feet into here, that term goes away, so the moment at 4 feet was 180, so the constant has to be 180 to make that work. Okay, so here is my complete expression for moment as a function of x, and it's parabolic. So if we put in 10 feet, we better hope that this thing goes to 0, because the right hand support does not apply moment. So if you evaluate this at 10 feet, it has to go to 0, and it does. So that's our check. So we have, when we have a constant, this is a trend to think about, when we have a constant distributed load, we end up having a linearly increasing shear and a parabolically increasing moment in response to that. Okay, one more example. We got another beam, and this has got a little bit more complex loading system here. We've got a hinge force again at A at the support, and we got just a single roller support at B. We got a point load at 3 meters. We got an upward, we have an axial load. This arrow is just indicating this is where it's located. We have an axial load that we pick up at 4.5 meters in the amount of 2 kilonewtons. We have a point applied couple. Somebody's grabbing the beam and just twisting it at that point, equal to 3 kilonewton meters. And that's being applied at a single point at 6 meters. And then at that same point, we start applying a distributed load that peaks out at 10 kilonewtons per meter. It starts at 0, and then the beam ends at, it's 9 meters long. So we want to write expressions as a function of x for shear and bending and axial force all the way along the beam. So we are going to apply the same principle we did before to each one of these sections. We're going to go from the left hinge to our applied point load. We're going to go from that point to where we have another applied point load. And then from that point to where we have a point applied moment, and then the remaining section where we have all of the above plus a distributed load. So we'll have 1, 2, 3, 4 sections. So we will apply those same relationships between distributed load, shear, bending, putting a cut section of the beam. It's going to be a lengthening section, so we're going to start with the left-hand side being very small, and it's going to grow and grow and grow until it's the whole beam. But we're going to have 4 different distinct areas of concern, and we are going to use those areas evaluated at the right-handmost limits as the starting points for the section over, the left-handmost limit of the next section. Okay, so as usual, we're going to start with the support reactions. Now we only have one externally applied load in the x direction at 4 kilonewtons, going in the positive x direction as defined by our coordinate system here. A is the only place where we have the capability of applying a horizontal force opposing it, so we know that A sub x is negative 4 kilonewtons in the I direction. We're going to want to get an equivalent position and load for our distributed load, so we're going to cheat a little bit, and we're going to use our triangle area under the curve relationship and say our distributed load equivalent is equal to 1/2 base height of our load function here. So that's 8 kilonewton per meters h, and the base being 3 meters, 1/2 of that. And we know that it's located at 2/3 of the way from here to here. So it's located, the equivalent of the distributed load is located really at x equals 8. So it'll be right about here. So here's our FBD for our beam to get A sub y and B sub y with all of the applied loads are 2 kilonewtons vertical, our horizontal 4 kilonewtons, our 3 kilonewton meters point moment, and then our resultant for our distributed load at 12 kilonewtons being applied 1 meter from the end. So if I crank through those conditions of equilibrium, setting the sum of the forces in the x equal to 0, the sum of the forces in the y equals 0, and taking the sum of the moments about point A, I get my support reactions. So I get 11 kilonewtons upward at B, and I get 3 kilonewtons upward at A. So when I finish with my expression for shear, I know what I hope that that final expression for shear is going to be when I drop in x equals 9 meters. I hope it's going to give me 11 kilonewtons. And then I'll use my 3 kilonewtons as my starting point for section 1. Okay, again, here are my intervals. X is equal to or greater, and that's very important. It's equal to or greater than 0, but it's less than 3. And that means by stopping short of 3, I haven't included this. The next section will be 3 meters, x greater than or equal to 3 meters, which means at that point I will pick up this point load, and I'll go to just shy of 4.5 meters, which means I won't pick up this axial load, and so forth. So for each of these intervals, my left-hand side will include any point loads, point moments. My right-hand limit won't. So I'll pick them up in the next. Okay, so I start with my first interval. I have at hinge A, I am applying 4 kilonewtons negative in the horizontal direction, and I have 3 kilonewtons vertically upward. And here's my full complement. I define point Q here on the face. Here's my full complement of forces and moments that the remainder of the beam's applying. So I can say right now that the axial force anywhere in this section as a function of x is a constant 4 kilonewtons. So this n is yanking at 4 kilonewtons. Shear force is also going to be a constant because I don't have a distributed load. And if my shear force is defined default positive upward, it's going to be negative. So it's going to have to be pointing downward to balance this. And moment is going to be defined as 3 kilonewtons times x. I could go through and show how the constant of integration is 0 based on the fact that there's no applied moment here at x equals 0. So I have my 3 expressions. My next interval of interest is going to be picking up at 3 meters. So if I evaluated my shear at 3 meters, it'd still be negative 3 kilonewtons, and the moment at 3 meters will be 9 kilonewtons. So those will be my starting points for the next one. Okay. So looking at our next interval, we've now extended the beam out. So we can see that our point Q is now kind of, I've drawn it solidly in between 3 meters and 4.5 meters. So now we've got another point load. We've got another one of our applied loads on the beam. And then of course we have our applied internal forces coming from the remainder of the right-hand side that we're not seeing. So our normal force here is still going to have to be equal to this one because nothing else has happened to attenuate it. Our shear force, we don't have any horizontal, we don't have any distributed loads. So our shear force is just going to be a constant, and it's going to have to be equal to the sum of all the other applied point loads or their resultants. So that would be, we've got 3 kilonewtons minus 2 kilonewtons, so we have a resultant of 1 kilonewton upward. So V is going to have to be negative 1 kilonewton downward to balance that. So our shear load dropped. It stayed in the same direction, but it dropped in magnitude due to the influence of this point load. So if we integrate our shear expression with respect to x, we get moment, and we're going to integrate starting here at x equals, effectively at x equals 3. Excuse me. And we can use our original expression for shear as 3 kilonewtons and then integrate piecewise and get 3 kilonewtons times x as the negative integral plus negative So we integrated separately the effect of both of these point loads to get an expression. And we can show that we could have just integrated this effective one over some limits of integration. But we get the same expression. We end up with the moment at point Q anywhere as being 1 kilonewton times x plus 6 meters. So this is a little bit more complicated way of doing it with the indefinite integrals. So we went back and we integrated the resultant moment due to the need to balance these two and the effect of the shear force in different regions. So we basically applied, going way back to we applied this due to the shear force that we needed to oppose our hinge support over one set of x intervals, and then the resultant shear force we needed past the 2 feet over a different interval. And we picked up those intervals with these x positions. And so here's our expression, resultant expression for moment, really anywhere from 0 to the cut face. Okay, and if we wanted to put in our next interval at 4.5, we just have 4.5 there, plus 6, so 10.5 times 1 kilonewton. So we move into region number 3, where the only difference is we now have the applied 4 kilonewtons positive to balance our axial load, so n drops to 0. Nothing else has changed, so this expression and our moment about point Q is also unchanged from up here. So the only thing that happened was orthogonal to V and M, so it didn't affect those. So the big changes come in this last region for x greater than or equal to 6 feet, less than 9 feet. So here we've got our distributed load. We've got an expression for it based on its magnitude and at points relative to our x equals 0 coordinate system. So here's our distributed load. If we want to get shear force at our cut section anywhere there, we're going to end up using our shear force from the previous section plus the contribution just to the distributed load. So we have our -1 kilonewtons coming up from the previous section, plus what V has to be to balance the distributed load just within this section. We could use this also if we wrote a total expression for V sub x. This would end up having been the lower limit of integration. So we've got our axial force is 0, our shear force is picking up from the previous section, plus we're going to have the integrated contribution of the distributed load. So we can evaluate that. So that equals -1 kilonewton plus, dropping in our expression here for Q sub x. Crank through the integral. We start ending up with some squared terms. And final expression for shear anywhere is going to be parabolic, concave up, so getting really high. We can drop in and again this was just literally cranking through the math, just evaluating this integral and then adding this front term, keeping all the signs straight. So we can plop in an x equal 9 meters and evaluate V at x equal 9 meters and make sure that it equals 11 kilonewtons, which it does, so that's a good check. And now we're going to go the long way, and this is the last time we'll do it a distributed load for a moment this way. but we can look at the effect of the distributed load on moment without necessarily using our v sub x, which would have been a different way of doing it. As you can see, there's a lot of different ways, and this example really is a bit, I'm going to say, the difficult way of doing it. We'll go through another more elegant example or two that I would rely on, but this is a way of doing it which is totally equivalent. So if we are going to look at the moment at point Q that we would have to be applying from the rest of the beam, we'd have the moment up to point x equals 6 meters. We'd have the applied moment, that 3 kilonewton meters, and then we would have the increasing result of our distributed load, which we can write this way. So we can get an actual expression of the distributed load in terms of x, which we did when we were doing the hinge expression, at least a little bit. And we can get the moment due to that. Again, putting it at R1, continuing through, and then picking up in our last expression, hand adding the effect of the moment due to the increasing shear force and the point applied moment plus the moment equivalent of this distributed load. Okay, so this is literally using the old R sub 1 equivalent, but this time we're keeping it open in terms of x. So let you guys step through that. And we can check it at x equals 9 and show that it goes to 0, which correlates with the roller left support, which can't impart moment. So this is actually a very correct but very cumbersome way of stepping through each one of these regions. We did an awful lot of hand addition of contributions to moment from shear, picking up other regions. We didn't do this so much in terms of continuous integration and limits of integration. And well, this is valid, and you can see that it checked. And I'll note that that we have the correct order of terms. We got a moment expression that's a cube term now. If we had a shear that was a parabolic, that makes sense. It is a lot more elegant to do this in terms of limits of integration using definite integrals, and so using the ending point from one region as the lower limit of integration for the next interval. So we're going to take a break and pick up with example 4.22 and look at using an equivalent but a little bit different approach to these that might be a bit easier.